So let's say we have two long straight wires that are parallel to each other. One of them is carrying a current of 2 amps and one is carrying a current of 4 amps. I would like to know the magnetic field, the vector. So I want not only the magnitude but the direction of the magnetic field at a point smack dab between them. So right in the middle.
Question then, will they cancel one another? Will do magnetic fields cancel each other out?
If they're in opposite directions, they can, yes. Because it's a vector. So we simply need to find the magnetic field for wire 1 plus the magnetic field for wire 2. And yes, if they're in opposite directions, they can, when we add them vectorially, they can cancel. Okay. So wire 1. It's a long straight wire, so this mu naught I1 over 2 pi r is going to work just fine. Mu naught is 4 pi times 10 to the negative 7 Tesla meters over amps. I is 2 amps. R is half of our 25 centimeters, 0.25 over 2 meters. Unit-wise, our meters cancel, our amps cancel, leaving us with Teslas, which is good. That equation, though, only gives us the magnitude of the magnetic field. We need the direction as well. Direction is actually really easy to find if you use a right-hand rule. For any wire, again, it must be your right hand, hence the term right-hand rule. If you put your thumb in the direction of the current, your fingers show you which way the magnetic fields circle around the wire. So here, if I put my thumb in the direction of the current, on the left side of the wire, my fingers are pointing out of the board. So the magnetic field is coming out of the board on the left-hand side. If I wrap around so I can have my fingers on this side of the wire, my fingers will be pointing into the board on this side. So the magnetic field's making circles around the wire. It's coming out on this side, in on this side. The point we're interested in is on the right side of the wire. So the direction of the magnetic field B1 at this point is into the board, which is the negative K direction. If using X being horizontal, Y being vertical, Z would come out of the board. So into the board is negative Z. Okay, let's see. I get 3.2 times 10 to the negative 6. So I'm just going to write that as 3.2 microteslas. And it's negative K hat is the direction. B2. Same equation. U naught is 4 pi times 10 to the negative 7 Tesla meters over amps. The current for B2, though, current 2 has 4 amps of current. It's also a distance of half the 25 centimeters. So its magnitude is basically going to be twice as big. Yes, direction will be different. Putting my thumb in the direction of the current on the left side of this wire, my fingers are coming out of the board. So the magnetic field on this side is out of the board, on this side it's into the board. The magnetic field coming out of the board would be positive K hat. So the net magnetic field positive. You don't really need to write the positive down. By not writing a negative, it means positive. The magnitude of the field is 3.2 microteslas. The direction is positive K hat, so out of the board. That 4 amp wire, that second right-hand wire, is creating a larger magnetic field because it's carrying more current.
So if you had two equally amped up wires, I'll put it that way, there is a line that has no magnetic field in it, but it gets weird as you go.
Yeah. Exactly. So there would be down that center line, if both wires have the same amount of current, there would be a line down the middle where the field would be zero.
Well, and we've got one here too, it's just...
Certainly, there is a place. Exactly. There will be a place closer to the 2 amps where the field will be zero. That's exactly right. So the nice thing is, any long straight wire, you can use the result. You don't have to reintegrate to get the result. We've integrated, we're done. No use reintegrating if we know the result.